Thank you very much, Mona and Jose, for the kind introduction, and also, of course, for the invitation. Give me the opportunity here to speak about some of our recent work. So I'm actually talking about some work that was also highlighted in a recent Laserlab-Europe newsletter with the focus lasers and the universe. That will be the main topic. And so, as was said, so our group is working mainly in the field of laboratory astrophysics or astrochemistry. And then today I would like to focus in my talk on a rather new method that we developed where we combine chemical reactivity studies, so not too much physics anymore, but more chemistry, with spectroscopic probing. And a recent, somewhat surprising result on a low temperature formation pathway towards so-called polycyclic aromatic hydrocarbons. You see an example here, which are actually complex molecules that are found in space. So to do these experiments, our group is actually operating a cryogenic ion trap end user station, which you see here at the FELIX Laboratory, which is part of HFML FELIX. And I would like to start very briefly with giving you a small introduction to our facility for those who are not familiar with it. So HFML FELIX, it's a long name. It stands actually for High Field Magnetic Laboratory and Free Electron Lasers for Infrared Experiments. And it is a collaboration of Radboud University in Nijmegen and NWO, so the Dutch science funding agency. And it's a research facility really for national and also international users with a very distinguished also in-house research program of which we are actually part. So we do have very high field magnets, 6 of them up to 38 Tesla. That's one part basically of the facility, but we also have a total of 4 very intense, powerful infrared and terahertz free electron lasers that cover really an unprecedented range of around 2.7 to 1500 micrometers. And I will, in this talk, mainly focus here on work done, or focus only on work done with the free electron lasers. But we do both, and there's also a combination between the two actually within the facility. So our lasers, we actually have 4 of them, and it is just a very brief schematic outline. So it's free electron lasers, so we use undulation of free electrons that are accelerated to generate, no, not X-ray, but infrared radiation, very bright pulsed infrared radiation. And with the 4 different free electron lasers we have, we can actually cover this very broad range. And we can also tune actually over continuously, basically over an octave of frequency with one of these free electron lasers that provide us then the radiation that we use for our experiments. And here is another, just a few of the characteristics that we have of our lasers. So we can use 3 in parallel. That is the FELIX or flare leech lasers. Really the main points, once again, are the wide tunability, also the very high intensity, so that we can do experiments that are not possible with tabletop laser systems. We can also actually generate ultra-short pulses, although in the experiments I will present here, we do not use this specific characteristics. And we mainly, for our experiments, use the main FELIX lasers. It's 2 free electron lasers that we can choose from that cover really this range from 2.7 to 150 micrometers, or for the terahertz people, so it's around 2 to 120 terahertz. And we have a pulse structure, and we have really high output powers of the 100 millijoule per macropulse, which comes with around 10 hertz. And I'm happy to answer any more questions afterwards in the question and answer session if you want to have a bit more details about it. So these lasers are actually in our basement, but they're coupled to a lot of different user stations that we use, but that also our users use. So there are 15 that are then named here with some flexibility to bring your own experiments. So we have a lot of actually gas phase end user stations that are really dealing with, let's say, molecular spectroscopy, reactivity studies. And I will talk about one of them, station 6, that's the cryogenic ion trap that we do operate. And of course, I also would like to mention that we are also embedded very widely, not only nationally in the Netherlands with a lot of different universities with which we have collaborations, or to come, people who come here as users, but we are also part of all the very important ongoing networks, both in the field of high field magnets, but also, of course, of laser systems, including also Laserlab-Europe. So let's go now to the actual science part of my talk. So what do we do with these nice lasers? I have here a very brief outline. So I first, since we're working in astrochemistry, astrophysics, I would first like to start to give you actually a brief motivation. Why are we actually interested in these large, complex molecules, these PAHs, polycyclic, aromatic, hydrocarbon in space? And then briefly introduce the toolbox that we have. So that's this cryogenic ion trapping and action spectroscopy. And then give you this example of how we study the low temperature formation of some of these complex molecules under conditions that are mimicking those actually in space. And so as a part of motivation, so when you think about astronomy, the main thing that you perceive with your naked eyes when you look into the sky are stars. So you see here different constellations of stars, and I picked here the very famous Orion constellation that was very nicely visible during the winter now over all of Europe. But if you have very good eyes, you might see here a little blurry object also within this Orion constellation. And that's actually the so-called Orion Nebula. And if you zoom in now with, let's say, some of the best eyes that we have, this Orion Nebula shows up in all its beauty. So this is a picture, actually, measurement from the Hubble telescope of this Orion Nebula, shown here in different colors. And these actually regions are actually what we call molecular clouds. So these are very fast amounts of gas and dust that are getting together. And astronomers are actually very interested in these regions because in these rather dense or denser regions of space, that is where new stars, new planets are forming. We would like to understand how that is happening. And also, of course, within these planetary systems that might be formed, there might be also, of course, the new origin of life, apart from what we see here on Earth. So we are interested also in the complexity of molecules, in the chemical pathways that we can find in these regions here. Because we know actually that these regions are very rich in chemistry. So we see a lot of actually molecular species that are formed in these regions by not only taking these kind of beautiful pictures here, but also do spectroscopy. So with the telescopes, we can actually record spectra of these regions. And this is here actually an example from a former mission, the Hi-Fi Herschel, the Herschel telescope with the Hi-Fi detector. And what you see here is really a spectrum in the now in the far infrared terahertz region. And all these lines that you see here belong actually to different molecular species that are recorded here in this Orion Nebula region. And you see, we already have identified quite a few, like carbon monoxide, water, but also more complex species like methanol or dimethyl ether that are here identified. And this is what astronomers already call complex molecules. So everything with larger than four atoms is for an astronomer a complex molecule. But we can actually go even to a bit larger systems than that. But in order to actually identify these kind of species in space, so what we get, of course, is only this kind of spectra from the telescopes. We need to know from the laboratory as a first prerequisite a very accurate spectrum of this under laboratory conditions. So we need laboratory reference data, which we call the spectral fingerprint of these molecules, in order to be able to then identify new species in these regions, and ultimately, of course, to get then kind of chemical inventory of these regions to ultimately then understand the chemistry happening. So there is already a lot of molecules actually detected in this region and other star-forming regions, but also around late-type stars. So we could really speak about a molecular universe, and what is plotted here is just the number or the cumulative number of detected different identified species as a function of year. Stopping here at around 2020 already, I think, so I should update this. And you see here this big increase. That is actually when radio astronomy came into play. So most of these species in these kind of colder regions of space are actually detected by radio astronomy via the rotational transition. But every year there is around 45 or so, or up to 7 new of these species added to this list, because telescopes get better, but also laboratory data gets better. And once we have identified these species, we cannot only, make a table and say, okay, like a stamp collection, what we have found, but we can actually use this then to really probe the chemical composition, understand the chemistry, but also learn something about physical conditions in these regions, like temperatures, pressures, or how these molecular clouds might start to go back to form and actually start. So this is the one part. It's more about radio astronomy that we are interested in. But also, if we go back to this picture that I had here of the Orion Nebula, we also have other frequency regions that are important for us to study these kind of star forming, but also other regions in space. And very recently, at the end of 2021, a new very sensitive observatory has been launched, the JWST Infrared Observatory, and we are actually involved also in studying parts of this Orion Nebula, the so-called Orion bar with JWST, and this is really working now in the infrared. So you see here first picture of, again, a zoomed in region here within Orion, and that is a so-called photon-dominated region. So that's a region where a lot of UV, far UV photons are present. So that also triggers a lot of chemistry, but also, of course, is a very, let's say, chemically active region that we would like to try to understand. And this is in the infrared, and again, we can not only take the pictures, but we can also take a spectrum. And that is what you see here. And this is not from JWST yet. That's about to come out very soon. This is from ESO, but here you see the infrared spectrum of this Orion bar region that I showed before. And this is here actually a spectrum taken of another region, which is actually an old type or a planetary nebula around a dying star. And what you see here is that, so you see here the wavelengths is from 3 to around 20 microns. And what you see here, all these emission features that are here highlighted in red, these are actually emission features that are attributed by now to emission of these so-called polycyclic aromatic hydrocarbons, representing different vibrational modes of these species, which are all a bit clustered together at similar frequencies. And the idea is now that that there is a little bit of, first of all, variety, of course, in the spectra, but first of all, they're seen in a lot of different astronomical environments. So they are really presenting a very big part of the carbon chemistry or the carbon repository in space. And why they are actually here seen in emission is the idea, so that's the so-called PAH hypothesis, is that this infrared emission comes about from the absorption of these PAHs of a UV photon, that then is actually, so the energy that these molecules get is then actually emitted back, so it's cooling down via this emission of infrared photons. And there is a slight variation here in these spectra in different regions, and that is typically attributed to a change in both the charge state of these species, but also the size, hydrogenation state. But there might also be substituted species in there. So it tells us a lot also about the composition of this PAH family, this spectra, and also the conditions, of course, of the source that we are looking at. But again, for interpreting these spectra, we need actually infrared spectroscopy to make a comparison between the laboratory data and the astronomical observations. But what is also very interesting, of course, to know, so how do these PAHs actually form? And that is what I get back to in just a little bit. So these PAHs are not only present in these, let's say, gas phase or interstellar medium regions in space, but they also thought to be present in planetary atmospheres. This is here actually a mass spectrum, what you see here, taken with the Cassini probe and of Titan. So Titan is Saturn's largest moon. And you see here a lot of different mass peaks that are here actually rather small molecules, let's say up to a mass of a charge ratio of around 100. But these are all hydrocarbons and or nitrile species. And what we think is that, or what is thought is that these are basically the precursors then that later form also these polycyclic aromatic hydrocarbons when you go a bit deeper into the atmosphere of Titan. And these are then the building blocks, so to speak, of aerosols, clouds, and maybe these so-called tholins in Titan's atmosphere, which are actually responsible for the the orange hue, the orange color that we see when we look at Titan. But also here, the formation pathways are yeah, going from the smaller blocks to the larger blocks is not completely clear yet. And we are here at maybe temperatures about around 150 Kelvin. But very recently, actually, what happened is that these PAHs were actually very unambiguously identified. Again, now via radio astronomy. So you see a few nice radio telescopes, so two groups in the US and in Spain mainly. They were able to identify very specific polycyclic aromatic hydrocarbons, these very small species or other aromatic rings, with these radio telescopes. And in fact, they did this in now in a molecular cloud that is very cold. So I got this down here around 10 Kelvin. So it's a very cold region in space. And the question is a little bit, how do these PAHs actually form under these very low temperature conditions? And that is a little bit where we come in, which we would like to investigate. So what is thought about, or what people think is how our PAHs form in space? There's one hypothesis that actually says that we have bottom-up processes starting from really atomic species like carbon, hydrogen, and then you have basically combustion chemistry happening in very hot regions of space at high temperatures where different mechanisms have been proposed. So I don't want to go into detail, but it's been principle that you start with hydrogen extraction, acetylene addition, reactions that you start from smaller building blocks and then form more and more rings to these kind of species. And the different of these processes are proposed and studied. But if we now have these rather small PAHs seen in this cloud, in these very cold clouds, there's a little bit of a problem because all these reactions that have been proposed, I mean, they come from combustion, so they are actually involving, and it has been studied in the laboratory and by theory, they often involve very large barriers. So they only happen in very hot environments, like circumstellar shells. So these are shells of molecules of gas and dust around very late type stars, which can be very hot. But then the question is, how are they actually transported then to these colder molecular clouds? So in the basically next cycle, and then these molecular clouds condense again to form new stars. And it is thought that this transport from this region of origin to then this region of basically then consumption for new stars, that is very harsh and they might not survive. So what is thought is that we need to have some formation pathways that are actually happening in these cold regions also. So the cold means really in these clouds that I showed you a few of, dense clouds, it's only 10 Kelvin, maybe up to 100 Kelvin in this really in regions of Orion that I showed before. Titan's atmosphere, well, where the chemistry is happening, is maybe around 150 K. We also have very low density, so it's only 100 to like a million or so particles per cubic centimeter. We have kind of single collision conditions, so we need to have some very let's say efficient pathways that are actually happening under these conditions. And what we think is happening at these low temperatures that are relevant in these cold molecular clouds is that we can have radical neutral reactions. So there is a lot of people studying also these type of reactions. But what could also happen is that we have ion molecular reactions, and these reactions are often barrierless or have very low barriers, so that they can proceed even almost at the collisional rate at very low temperatures. And that is what we study, for example, in our instrument, that I'll show in a little bit. But the fact is that we might know that these reactions are, let's say, are relevant in these regions. But of course, again, we need to first study them in the laboratory. So we need to kind of input, for example, for astrochemical models that try to understand then the abundance of all these different species in order to really pin down the pathways that are important. With this, I would like to go back once again to this detection that I showed before from this radio astronomical observation. So that is here an example of one of these species that were detected. This is basically naphthalene with a cyan group, cyanonaphthalene. And what one can do now from these observations is that one can obtain an abundance. So how much of this molecule is in the specific region in this TMC1 cloud that they were looking at. And this is what is shown here. So you see here, that is the ratio versus H2. This is the column density of the species. That is what is observed. And these lines here, that is what comes from different astrochemical models. And when you compare that at the different time steps here, you see that actually at the time where we think that this cloud is at the moment, the orders of magnitude between the prediction or the simulation of the abundance and what is actually observed. So there can be different reasons for this. So maybe we don't understand the source very well, but very likely it is that we don't have all the reactions in the network that are needed to actually explain that formation. And so we are focusing now on trying to provide some of this data for ion molecule reactions, which is one of the class of reactions very important in these regions. Because of the conditions there, we can think about bimolecular reactions or radiative association reactions that are important in these low density regions of space. But we also might come across, and we did actually, about like thermomolecular reactions, where you have the three-body collisions that take away some of the reaction energy. But this is also maybe important in these denser regions like the atmosphere of the Earth. So what did we now exactly do? So we picked a kind of example or one reaction that we want to study now in quite great detail. And that is also the one example that I now want to use here to show you what we can actually do. So this pathway that we wanted to look at was a reaction between the pyridine cation. So that is basically heterocyclic aromatic ring molecule. That's a cation here. And we wanted to look at the reaction with acetylene. So basically giving it more carbon units in the hope that we then form a second ring. So go to this throws to this polyaromatic hydrocarbons that we see in space. This had been studied before in different groups by mass spectroscopy. And it was seen that one forms larger molecules in this reaction that might actually be something like this quinolizinium molecules, or a two-membered ring, two-cycle ring here, as shown here. But in these studies, you don't really know the structure of the molecule you form. So what is happening is it could also be that you might add these acetylenes here, and you see then, okay, you add one and you add two from the mass. But why? It could also be that we just have some sort of dangling acetylene units that are hanging here on the pyridine molecule. And the question is now, and that is what we set up to, can we actually do, first of all, the same kind of kinetics? So can we get rate coefficients for this reaction at the low temperatures that are needed? And then actually, can we use spectroscopy with our infrared lasers to elucidate the structure of both the intermediates that we might form, but also the products? And I can already tell you, yes, we can. And we do this by using a rather multifaceted experimental approach. So we do also do mass spectrometry in our instrument, but we also study then the ion molecule kinetics, so really the formation of these molecules over time to get rate coefficients. But then we use infrared action spectroscopy to get the structures. And then we use also quantum chemical calculations to compare, to get to the structures, but also to try then to unravel this pathway. And that's a reminder, this is the reaction that we want to look at, and we want to know if we form this kind of molecule here. So how do we do this in detail? So I will just briefly walk you through our experiment so that you can know, you know what how we get actually to the results I will show. So what we use is a so-called cryogenic ion trap instrument, of which you see here a sketch that is actually now an end user station at FELIX. It was developed, in fact, in Cologne in the group of Stefan Schlemmer, and then moved here to FELIX to be used by us and our users in combination with the FELIX lasers. So in this setup, it has a few basic parts. We need to start, of course, with making the ion we are interested in. We can do this by different means, but the workhorse in our instrument is actually an electron impact source. So we bombard a neutral molecule with electrons and vary the energy. We use a rather sophisticated source that is actually already a trap, but that doesn't matter too much for what I'm going to tell you now. So for example, if we do this and we put in neutral pyridine into the source and the electron, we can record then a mass spectrum of whatever comes out. And you see that we form both the pyridine ion. We also form a protonated pyridine, which we're not so interested in right now. And we also form fragments, so that in itself is also quite interesting. But for this experiment now, we wanted to look at the reaction of the pyridine cation. So what we do is we then mass select the pyridine cation, which is NZ79, in a quadrupole mass filter, and then we guide it here around the corner, but into our cryogenic ion trap. And the cryogenic ion trap is actually a 22-pole trap. So there's 22 electrodes. And we do have this kind of trap, which was developed by Dieter Gerlich and then further developed by Stefan Schlemmer in Cologne. We use this kind of trap because in such a trap, we can very efficiently cool the ions to the ambient temperature of the trap by using a buffer gas. So this whole trap is mounted on a on a cryogenic cold head, and then we pulse in, for example, helium. And because we have this large field-free region in this trap, we can then in collisions actually cool the ions both internally and also kinetically to the temperature that we are interested in. And it is down to 4 Kelvin, but we can also operate at different temperatures. So for the reactivity studies, then let's assume we have now a pyridine in here. We work in this case at around 150 Kelvin, so a little bit hotter to not freeze out the acetylene, basically. And then we want to study this reaction, and what we can do is then add basically our neutral agent, the acetylene, here to the trap at a constant flow, at a constant number density, and then we really, as a basic chemistry experiment, we follow then the decline of our parent ion, the pyridine, over time, and follow also the growth of whatever intermediates we have or end products that we see. So we record this. We have single ion molecule conditions, or sometimes also three-body conditions, and we can then infer by fitting our data to this then the rate coefficients as a function of temperature. But this is something that you can do, and that's already quite nice. But what we now also want to do is that we want to know the structures of whatever we form here. So for this, we do this reaction over a certain time, and then at some point we use our lasers to actually record a vibrational spectrum of the molecule that we have formed. Sorry. We do this by using different infrared action spectroscopic schemes, and that allows us really then to get the structural characterization by comparison with quantum chemical calculations, and helps us then to elucidate really the pathway. So the spectroscopy we do then, so told you we do the reaction first, and then we want to do the spectroscopy. We can do the spectroscopy when we are very cold using so-called infrared-predissociation spectroscopy, that we could, for example, use if we want to know first the structure here of our primary ion, so the pyridine ion. And that works in the following. So if you have very low temperatures, we now use our gas pulse. That can be helium. It can also be a mixture of helium and neon. And what happens is that at these very low temperatures, we will actually form complexes of the ion with the rare gas. So we form complexes of the pyridine, in this case, with helium or with neon, which is then stored in the trap. And then we irradiate with the FELIX lasers. And what is happening is that whenever we are resonant with a transition of our molecule, we actually break the very weak bond here to our rare gas tag. So that's also called tagging spectroscopy. And then we see actually a decline then in the number of our complexes that we have formed as a function of the frequency. So that is what you see here. If we detect now the complex, we see this, and this is basically then a single photon, relative close to single photon absorption spectrum of the bare ion that we had used in the first. This we can use when we are very cold, but for the temperatures that we use here for the kinetics, we are a bit higher, so we will not be able to form these rare gas complexes. We can use another very well known methods, and that is infrared multiple photon dissociation action spectroscopy. For example, when we want to look here at this formed product of higher mass. And that is basically a method where we rely on the absorption of multiple infrared photons. So that's not really a cascade a process, but it's basically a process where we absorb the first photons, then we have energy redistribution, so we heat up the molecule, and then we are able to absorb up to 10, 50 or so different infrared photons until we really reach the dissociation limit of this molecule. So we have a dissociation, and in that sense, then we lose our primary ion that we want to look at, and we can again record a spectrum now in this way. And that is what we have used. So in the first step for this reaction that we want to study at, we wanted to know if we really form the pyridine cation in our source. So it could be that we instead form not this, I usually call it canonical pyridine cation here, that retains the structure of the original neutral molecule, or if you form some of its distonic isomers, where basically one of the hydrogens is actually moving from the ring here to the nitrogen side, and which are actually lower in energy than this one. And what you see here is now in blue the actual spectrum that we measured with this tagging spectroscopy method that I just introduced. So that is in all these panels, and then we compare this to a quantum chemical, in this case density functional calculations on the frequencies, and this is what you see here as these kind of sticks. And then we basically try to find the best match. And what you see here is that we really have the best match for this canonical pyridine. We did see that if we increase the energy a little bit of our ionization, that we might form a little mixture here of this alpha distonic. It's called pyridine isomer, where the hydrogen has moved here to this alpha position. But we are quite confident that most of what we have in our trap in the beginning is this kind of the cation that we're interested in. So then we can go further and then look at the reaction. So what you see here, as a reminder, here's the reaction we want to study. That is just the mass spectrum of the content of the trap after a certain time, where we have added the pyridine, cooled it down to this 150 Kelvin, added the acetylene, and then we take a mass spectrum of it before. And we see here that, and this at a rather low pressure, we mainly see here the formation of two intermediates. That is just the addition here of the acetylene, and it's a reaction where the acetylene adds to the pyridine, but the hydrogen is also. So that's already nice, but we can do this now as a function of time, as I showed you. So for the kinetics, we then follow the decline here, and then we also see here the formation of these two intermediates over time. And what is interesting, you see even that this intermediate, which is an association reaction, is even happening here after we shut off our gas pulse. So it's clearly a radiative association process that we see, which is interesting for astronomical conditions. If we add a little bit more gas or wait a little bit longer, we actually also see that we form a final product here, which has an even higher mass and corresponds to the addition of a second acetylene to our intermediates here. So that is this MZ 130, which was proposed to be this quinolizinium ion here. And again, we can look at this also time dependent. So here, under these conditions, the pyridine has almost reacted away at the start, but you see very clearly that here one of the intermediates is reacting away, whereas here the product of MZ 130 is formed. Whereas, for example, the other one, this 104 intermediate, is actually not affected by the second acetylene, say, so it's not reacting further. So it's kind of a stable intermediate, or even another interesting end product. We also see a kind of spurious reaction here to the protonated version of this guy, which comes likely from a self-reaction again with the pyridine. Okay, so that is nice. So from this we can get rate coefficients, reaction rate coefficients of these individual steps. But I promised that I show you also the structures of what we form, and that is what you see here. So what we have here is now again an infrared spectrum that we took of all these, of the three main products or intermediates that we see. So that's this 104 that we had, 105, 130. That's again an infrared spectrum taken with FELIX. That doesn't tell us that much yet, but what we now can do is compare it to all the possible structures that we might have for these intermediate ions and the end product, and that is what you see here. So we have here in red calculations for this kind of isomer for the 104 mass, same here in blue for the 105. and also for the final product 130. And we did a lot of different isomers, which I don't show all of you, but these are the best matches. So we can now clearly attribute the molecule or the ion that we form to this structure here. So we see that we have actually here had a reaction on the carbon, forming then these intermediate species. And also very clearly, we really now see that the end product we form in the end is actually a second two-cycle ring. So it is really a PAH that we have formed from this one cycle ring here. Of course, then we didn't stop there. So that was already nice, but we wanted to understand how that's happening. So what you can then do is do calculations on the potential energy surface to now try to understand how you actually get from your starting configuration here to your final product, this N-PAH phenolysinium that we see here. And there is actually a pathway that was also postulated before, which is basically just the attack here, without going into too much detail, the attack of the acetylene here on the N position in this pyridine, where you have then really a downhill reaction that's possible, an exothermic reaction to this product. So that would be nice, huh? But the problem now is that these products that we see here, so the structures of our intermediates, they are not found on this potential energy surface, because here we have a reaction on the nitrogen. So we expect these kind of structures here for the 105, and this one would be for the 104, but that's not what we see. So we have no evidence from the spectroscopy. We instead see that we have here the attack on the carbon, which is a little bit surprising. So we went back to the drawing board and also tried to calculate then a pathway, which we call a C pathway, where actually we have the attack of the acetylene now on the carbon. And this is what you see here. So it's a lot of detail, but in principle, we start again here. And we also again end up here with our end product. And the nice thing is, we also actually have on this pathway the intermediates that we do see when with the spectroscopy. So the ones we identified really experimentally. But you see, if you know a little bit about this PS, you see a problem here, because here at this point we do have a barrier. So we see here we start with a certain energy, but then to get to the end products and the intermediates, we would have to overcome this kind of reaction barrier. We actually don't know what the problem is. So we do experimentally see that we form these species and also the product. So we think that we have these two parallel pathways. It might be that we form here this pre-reactive complex that can then tunnel through the barrier. It might also be that the level of theory we used here, which I forgot to write down, sorry, in this slide, is not sufficient actually to explain this, so that actually the barrier might be lowered. But we are quite convinced that because we see it in the laboratory under the conditions of 150 Kelvin, that it is a reaction that will happen also in space under low temperature conditions. And we could even get the rate coefficients here, and we see that this rate coefficients to form these intermediates, they're quite large, so they're close to the Langevin value. So basically, upon every second collision in this case, we will form this molecule here. And here it's a bit slower because we have an association. So we think we found a very, very important pathway for the formation of these specific nitrogen-containing PAHs in space via ion molecule reactions. That is what is a little bit summarized here. So by combining now all the information that we have, we can come up with this kind of pathways from the pyridine, the acetylene, to these different intermediates. This one we could not identify spectroscopically, maybe it reacted too fast to the end products. We found this one spectroscopically, and maybe some evidence also for another form, the quinoline, where then now the nitrogen is incorporated here in the ring, but with a lot less intensity than the quinolysinium. So you might wonder, that's a very specific detail. Of course, it is important because this really gives input for these astrochemical models for different pathways on this very specific reaction now. But of course, we hope to do this also for a lot of other reactions that might be important. But basically, as a side effect, what we also get, of course, are the infrared spectra of these species that we either form as intermediates or as products. And what we found quite interesting also is that when you now compare the spectra of these so-called endoskeletal nitrogen-containing PAHs, where the nitrogen is here really incorporated in the middle here of the ring, that there wasn't that much known about them. But if we compare this now to, again, the astronomical observations, so this is now another of these spectra, similar to what I showed you before, seen in space. And what you see here is now our experimental spectrum in red here of this N-PAH family, and in blue now of a normal PAH where we don't have this nitrogen incorporated. And what you can clearly see is that we get a lot better matched of the a little bit, complicated to describe CC stretch mode that is seen in the in space when we have this incorporation of the nitrogen here versus if we just have a bare carbon ion. So that might be also dependent on, of course, on the size of the molecules. So we also did now some calculations because we don't have the spectra yet. So if you would increase now the size of these N-PAHs, so that's also shown here in red, versus the normal PAHs in blue, you also see for the pure carbon PAHs a shift now in the right direction here for the CC stretch. But you can also see that still for the N-PAHs there is quite a good match. So it might be one of the reasons why there is some variability here in the CC stretch region that we see in the space spectrum. One of many, I must say, but it could be one class of molecules that is there. And with this, and I'm sorry, Ramona, that I didn't stay in the 30-minute as promised, but I'm kind of almost done. So what I wanted to show you is that we have a nice experimental technique that combines spectroscopy and kinetics now to study reactions under really interstellar conditions. That with the example I showed you, we found actually a very interesting new class of these large organic hydrocarbons in space that might be out there and just need to be detected. And of course, we now plan to apply this to a large class of other important ion molecule reactions. And this was really only possible by this combination of the kinetics that we can do with the FELIX spectroscopy that is available at our facility. And I don't want to stop before thanking, of course, everyone involved. So I'm part of the FELIX infrared and terahertz spectroscopy group headed by our director at FELIX, Britta Redlich. But actually, most of the work I showed now in the example here is actually coming from our PhD student, Daniel Rapp, very good PhD student, together with also Aravind and at the time still a PhD, sorry, an undergrad student, Diane. So they did most of the work and most of the calculations. So I'm very happy that I'm allowed to show this here to you. And of course, I would also like to thank Stefan Schlemmer's group for all the support with the instrument and providing it. And we have a lot of theory support also for the different projects that we do from here from Radboud, but also across the globe, including Simon from Toulouse, who I think is here in the audience. And I would like to thank you for your attention.